we invite speakers from academia and industry to share their knowledge and discovery in specific areas of AI. Unlike other technical talks, these talks will be tailored to people without much background in AI. Therefore, they're fun to listen to and easy to follow. We hope that by listening to these talks regularly, you'll gain a solid knowledge of AI. Please help spread the word about Youth AI Talk. Thank you for your support of this educational and community service initiative. Please also consider visiting our website at youthay.org and sign up to receive announcements for other upcoming events like this one and resources. Also, if you miss any of our talks, feel free to also read the webinar summary that'll be released after the talk. We've hosted 20 fantastic talks since the kickoff of the Youth AI Speaker Series, and we're excited to introduce a new addition to complement our distinguished speaker series with this inaugural talk. We have a lot of exciting opportunities planned for 2023, so if you want to keep up to date with any upcoming talks or events, you can either follow us on social media, Eventbrite, or register on our website at youthay.org. So our speaker series covers important areas of AI, such as efficient AI, graphics, cognitive AI, finance, as well as different implications of AI. Our speakers are held in high regard in their respective fields, whether it be academia or industry. We have speakers from big players in industry such as Facebook or Meta, Microsoft, and speakers from top AI universities such as Carnegie Mellon, MIT, UC Berkeley, and Stanford. Replays of these talks are mostly available on the Youth AI YouTube channel, with the exceptions of a couple of talks which aren't available on YouTube due to company policy. With the Youth Speaker Series, we're excited to introduce the opportunity to learn about the unique journeys of young individuals who have begun to make huge waves in the field of AI. You'll gain insight into the challenges they faced, how they overcame them, and what motivated them to pursue a career in AI. Attending the Youth Speaker Series can be a source of inspiration and motivation, allowing you to picture yourself as a future AI expert, providing a window into what a thriving career in AI may entail for you. In the last Youth AI talk, Dr. Les Schmidt from the BRIIA Startup Accelerator Program spoke about the exciting intersection of entrepreneurship and AI and how new and innovative companies are building the future with AI. You're welcome to watch the replay of this great talk at our YouTube channel.
And we're really excited to also be able to announce our next upcoming talk coming around next April. And so that will be with under the topic of environment and sustainability, which we're definitely really excited to introduce as an additional topic to the Youth AI Speaker Series. Because if you've stuck around so far, we haven't necessarily been able to touch on the topic of the environment yet with our speaker series, which I think is especially important that we do now, especially with its relevance nowadays. And that talk will feature Dr. Lucas Joppa, definitely held in high regard in his industry along the lines of environment and sustainability. He was the first former chief environmental officer at Microsoft. So definitely highly recommend that you keep an eye out for that. Details will be posted later on at our Eventbrite, where you will be able to register for his talk in April. So we hope to see you for that as well. And before introducing Dr. Yang Song, I'd like to briefly go over the logistics of our talk. As we do have an audience watching from our YouTube live stream as well as on Zoom, we'll be doing Q&A through a platform called Slido, so that both our YouTube audience and our Zoom audience can participate in the Q&A session, because I'm sure we'll all have a lot of questions for our speaker today. And so you can either go to the URL, which will be pasted in the chat, or you can go to Slido and enter the event code 12359. So of course, feel free to submit questions throughout the talk, but we'll only be answering them in a Q&A session at the very end of Dr. Yang Song's talk. So definitely stick around for that to get your questions answered. And now to introduce today's speaker, Dr. Yang Song, whom we've all been waiting for. We're very excited and honored today to have Dr. Yang Song here to kick off our new youth speaker series as addition to our distinguished speaker series. So Dr. Yang Song is a research scientist at OpenAI, as well as an incoming assistant professor at the California Institute of Technology, Caltech. And Dr. Yang's research focuses on developing scalable methods for modeling, analyzing, and generating complex high-dimensional data with interests spanning generative modeling, representation learning, probabilistic inference, AI safety, and AI for science. Ultimately, he aims to develop methods that are both accessible and effective, building intelligent systems that can improve human lives and address problems that have wide-ranging significance. And as a researcher at OpenAI, his research accomplishments include developing a novel technique for generating images by training a network to unscramble noisy images, which has played a huge role in OpenAI's DALL-E 2, which has been used for AI-generated images that you might have seen these days, along with ChatGPT. And he has published extensively on these topics, which he will also be speaking about today. And before joining OpenAI, Dr. Yang received his PhD in computer science from Stanford University, and he obtained his bachelor's degree in mathematics and physics from Tsinghua University. Previously, he has worked as a research intern at Google Brain and Uber ATG, hosted by Raquel Erdogan, who is the chief scientist of Uber. And he is also intern at Microsoft Research. He has received numerous honors and awards for his contributions to the field. And as especially such a young expert in the industry, we're really excited to have him here today to share his insights and experiences to the audience. And so today, our brilliant speaker, Dr. Yang Song, will share his experience and thoughts as an emerging expert in the intersection of AI and diffusion models. So let's give a warm welcome to Dr. Yang Song. Thank you.
Thanks, Melina, for the nice introduction. So thank you for having me here. So before giving the talk, I would like to say that the talk contains no work that I'm doing on OpenAI, so it's not, it's a talk on behalf of myself only and shouldn't be viewed as like opinions from my employer. Okay, so today I will discuss about some recent advancements in diffusion models. And diffusion models are a very important family of techniques for generative AI, and they have powered numerous recent applications in generative AI. So before talking about generative AI, let me first talk about artificial intelligence, or AI first. So we as humans take pride in our intelligence because it is actually what distinguishes us from other animals. And in artificial intelligence, we hope to build intelligent machines or computers that can perceive the world like what we humans can do. Those machines should be able to learn quickly and should be able to plan ahead and should be able to act intelligently in the diverse environment in the real world. So in the past decade, we have seen lots of progress in artificial intelligence. Lots of progress are represented in the field of computer vision. So in computer vision, we hope to build software systems that can take an image and then generate deep understanding of the image. So for example, we hope to develop algorithms that can give us the category of any input image. And in addition, the algorithms should also be able to localize the object and to enumerate all relevant objects in the image and can even segment the boundaries of those objects. Those computer vision algorithms are very important AI techniques that are very useful for self-driving applications. So in self-driving, we use lots of AI techniques to detect cars on the road, to detect lanes. And we also need AI techniques to decide when to turn around and when to change lanes. If self-driving is successful, then this will be revolutionary for transportation and will generate huge impacts to the society and to our everyday life.
Doctor, sorry to interrupt, but I believe you're not screen sharing your slideshow.
Oh, sorry. So
no worries, that happens.
Okay, so does it work right now?
We can see it now.
Okay. Yeah, thanks for the reminder. So we can talk about self-driving, and another example is recommendation systems. So we also use lots of AI techniques in recommendation systems. I believe many of you have used TikTok before, and TikTok is famous for its successful recommendation systems, which leverages AI to ensure that it always recommends the right video to the users. And the latest AI systems are also immensely helpful for healthcare applications. They can be used to help doctors to diagnose disease and to assess the risk of patients for developing a certain illness. So those AI systems can be very useful for improving the productivity of doctors and to improve their accuracy. So in today's talk, I will focus on a subfield of AI called generative AI. The motivation of generative AI is to develop systems that can fully understand concepts that we oftentimes encounter in the real world. So how do we assess if a system really understands some concept? Let's take inspiration from Richard Feynman's code. Richard Feynman is a famous physicist who has made important contributions to quantum mechanics and also to particle physics. He said, "What I cannot create, I do not understand." So this was actually written on the blackboard right after he passed away. And how do we interpret the sentence? So if we claim to understand what an apple is, then according to his code, we should also be able to create a picture of an apple in our mind, which to be able to imagine its taste. So suppose we claim to understand what English is, then we should be able to write in English and to communicate in English. So generative AI takes inspiration from the code. Those are techniques that try to create things in order to deepen the understanding of the human world. So generative models are able to create new things by learning from existing things. So according to Richard Feynman's code, how do we know if a system really understands, for example, the concept of dog? We can ask the system to generate new pictures of dogs. So if the computer generates pictures like this, you can clearly see that some of the pictures are dogs, but the other pictures are actually muffins. This immediately shows that the computer program got confused with muffins and dogs, and it does not fully understand what a dog is. In contrast, suppose another program that can generate realistic pictures of dogs like this. Then we can clearly see that the program clearly possesses a better understanding of dogs. And then we can call it a generative model because it can generate new pictures and new data points. So how do we know if a generative model is a good one? A good generative model can create high quality new data points like pictures of dogs that have never appeared in the training dataset before. In contrast, a bad generative model will create data points that are irrelevant. Like here in this example, a picture of a muffin is irrelevant if you ask the model to generate pictures of dogs. So why do we want to develop those generative models? This is because they have numerous important applications. For example, suppose we have a generative model on realistic images. Then we may use it to convert a stroke painting of a picture to realistic images. And this is very helpful for designing purposes. Suppose we have a generative model on paintings. We can use the generative model to convert natural language description of the painting into real artwork. So in this example, the algorithm actually converts the description as of pentacles into two highly artistic paintings. And that this is also very useful for improving the productivity of artists. And suppose we have a generative model on medical images. We may use it to help machines get medical images from patients very quickly. So suppose let's consider computed tomography. in computed tomography, we need to use very expensive machines which generate X-rays to shoot through human bodies and then to generate the medical images. But as everyone knows, those X-rays are very harmful to patients. With a generative model which knows what a medical image looks like, it has the potential to reduce the amount of X-rays released by the X-ray machine, while without hurting the quality of those medical images. And those generative models are not only useful for creating images, they are also important for other data modalities. For example, with the generative model audio, we can use it to convert text into corresponding speech. And this is implemented in text-to-speech system. With the generative model on text, we can also use it to generate a full article given the initial sentence. And this is actually the underlying technique for ChatGPT and GPT-4. There are also lots of recent progress on generative models that have created lots of impact. For example, nowadays with the latest technique, which actually powered by diffusion models, we can create realistic pictures. And this picture is a panda man scientist mixing sparkling chemicals, which was generated by DALL-E 2, a software developed by OpenAI. And we can even generate videos using the same diffusion model techniques. And this is a video snippet generated by the imaging video model developed by Google. And those generative models can be used to predict radar maps for weather nowcasting. DeepMind researchers have developed a generative technique that surpasses human experts in terms of weather nowcasting. And those generative models are also useful for generating code, given some English descriptions of what you want the code to do. And those code usually has high quality and can directly run with the correct answers. And those can significantly improve the productivity of computer programmers. So now, before diving into the world of diffusion models, let me first give you a very basic introduction to the foundations of generative AI. So how do we create generative models? How do we create those fancy techniques that can produce new images or new video? Well, we first need to collect a large data set. This data set is called a training data set. So as a toy example, let's suppose we want to build a model that can create images of dogs. And for this purpose, we need to collect a large data set of dog images. And to make the discussion simpler, let's suppose we want to build a generative model and generates the first pixel of those images. So because we only want to generate one pixel, we can position those pixels on an axis. Those are real numbers on an axis. And since we have lots of data points, there are lots of such data points, and there are lots of points on this axis. So this constitutes our training data set. One very important assumption in generative modeling is that there exists a probability distribution and underlines our training data set. So this probability distribution tells us what's the probability of generating a particular data point. Unfortunately, we don't have access to this probability distribution. What we know are just training data points, which are actually samples from this distribution. In generative AI, the goal is to build a model to estimate this data distribution. So suppose we have a large family of different models, each model representing one probability distribution. We hope to find a single model outside this huge model family to make sure that the represented distribution is closest to our data distribution. We can measure the closeness between two distributions using our training data set. So after finding this optimal probability distribution inside our huge model family, we can do lots of cool things with this probability distribution. And the most important application is now we can generate new data points because we can use the probability distribution to create new data points that has high probability. And since this probability distribution has the capability to generate new data points, we call them generative models. However, it is highly non-trivial to build successful generative models. This is because in the real world, we want to generate high-dimensional data. A picture of a dog is a high-dimensional data. Generating the first pixel is not sufficient to producing the entire picture. We already know that the first pixel has an underlying data distribution, which can be depicted like this curve. To generate more parts of the picture, we also need to generate the second pixel. So the second pixel conditioned on the value of the first pixel is also a one-dimensional probability distribution, which can be represented using a similar curve. Now the joint distribution of both two pixels become a slightly more complicated. It is a two-dimensional figure. But two pixels are also not sufficient, so we want to use more pixels. In the case of three pixels, the underlying distribution becomes even more complicated. And as you can imagine, as we model more and more pixels, the distribution itself will become extremely more complicated. And this poses huge challenge to developing successful generative models for high-dimensional data. And clearly, the complexity of the data distribution can grow extremely quickly as we add more and more dimensions. So this is the reason why building successful generative models is very challenging. In practice, useful generative models should produce high-dimensional data like images, like a video. An image contains millions of pixels. This means it has millions of dimensions. A video can contain even more images, so the dimensionality of videos is even higher. And in all those cases, the data distribution is very complicated. And since we want to build a successful generative model, we have to create a family of distributions that are as complicated as the data distribution. And this is not an easy task. So to see how we can be successful in doing this, let's suppose we first build a very simple distribution. It's a general principle to start from simpler ones and gradually proceed to more complicated ones. So the simplest possible distribution here is a distribution called a Gaussian distribution. So a Gaussian distribution predicts the probability of data points using a simple formula and basically takes the exponential of the input, then divide the output by some constant. So the computation here is quite simple because it only amounts to one computational operation that computes the exponential function. However, Gaussians are too simple to represent the complicated data distribution. So we have to resort to more complicated techniques. And in practice, that means we need to use more layers of computation and more computational operations. So that corresponds to a deep neural network. So the solution to building successful deep generative models, to building successful complicated generative models is to leverage deep neural networks. And when we build generative models with deep neural networks, we get the so-called deep generative models. So the intuition is clear. However, the actual approach is complicated because representing a distribution is hard. Not all neural networks will represent a valid distribution. And this is because a distribution is highly restricted. The total probability has to sum to 1. So for example, if we want to predict the weather of tomorrow, and suppose tomorrow's weather can only be sunny already, then the probability of tomorrow being sunny plus the probability of tomorrow being rainy should sum to 1. And this turns out to be a strong restriction. We have such restrictions for high-dimensional as well. And therefore, building those deep neural networks that can represent distributions has become an important challenge in the mathematics of generative AI. And in this talk, I will discuss a way to eliminate this difficulty, which is the principle behind diffusion models. The diffusion models are also called score-based generative models for reasons that we will see very quickly. The idea of diffusion models is to work with a concept called the score function. So you can understand score function as an alternative way to represent a probability distribution. So given a probability distribution itself, a score function is a bunch of vectors and point to directions where the probability grows most quickly. So with the distribution, we can quickly get the score function by computing those vectors by taking derivatives. And vice versa, given the score function, we can also derive the underlying probability distribution using those small vectors. So the connection between score function and distribution is analogous to the connection between electric potential function and electric field intensity. So electric potential is a real number, it's a function that takes high-dimensional inputs but gives a one-dimensional output. The electric field intensity is a vector field, it's a bunch of vectors that gives the direction where the potential function reduces most quickly. So as physics have told us, the electric potential function and the electric field intensity function are equivalent ways to describe the same electric field. So the connection is analogous to the score function and the probability distribution here. So by working with those score functions, we can derive a principle for generative modeling. So first, we have collected a large data set. And second, we use deep neural networks to estimate the underlying score function. Those score functions do not need to predict probabilities, and therefore they are much easier to model with deep neural networks. In fact, they almost don't have any constraint. So you can use an arbitrary deep neural network to represent a score function. Unlike probability distribution, you have to carefully design the network to make sure it represents a valid distribution. So this is the major advantage for diffusion model here. And now the next step is to generate new data points by sampling from the score functions. So now, instead of sampling from the distribution directly, we hope to sample from the gradients of the distribution. And how do we sample from this vector field? A very simple idea is to first assume we have lots of random data points in the space. So how about just moving those data points by following the directions of the score function? So those points will travel along the directions of the vector field. Along the trajectory, the points will have higher and higher probabilities. But this is clearly not going to be successful because eventually all the points will collapse into several local regions that has the highest possibility of probability values. So this is not what we want. But the problem can be solved very easily. We just do the same procedure, but while we are moving the data points, we inject some random white noise. So by injecting the right amount of noise, we can make sure that those data points will eventually become valid samples from our score function. This technique has a name called longevity dynamics, and it is guaranteed to give us correct samples by following such a simple procedure. So now let's apply this framework to real image datasets. So we want to generate high-dimensional data like images. And this is the result of applying this technique naively. So the left shows you some images in the training dataset. The right shows you new images generated by this longevity dynamics procedure. So clearly, although longevity dynamics promise to give you the right samples, in practice, they do not. And clearly, there's something very wrong with this naive approach. And one important intuition to analyze this challenge is that longevity dynamics fail because our data is limited. So if you look at this figure, the middle shows you the true score function that we should estimate from dataset. The right figure shows the estimated score function by parameterizing a deep neural network and learning on our data points. So the model gives you accurate predictions for data points that are closer to high density regions. But in low probability regions, the estimated scores are very inaccurate. So this is possible because our data points tend to concentrate around high density regions. And therefore, we only get information from high data density regions, but no information from low data density regions from our data points. And this is why our estimated scores are not accurate in those regions. So this creates lots of trouble for longevity dynamics to generate new samples. And the recipe to solve this difficulty is to add noise to perturb our data point. So by injecting Gaussian noise to our data point, we can perturb the data points to fill those low data density regions. In the context of image generation, perturbation basically means we inject lots of white noise to make our image look noisy. So those noisy images will occupy larger portion of the space. And as a result, there will be smaller low data density regions, and the estimated score functions can be accurate almost everywhere. And this is very useful for sampling because it gives you direction for long-term dynamics to move to high density regions. But this is not a perfect solution because after injecting noise to data, we can only generate noisy data points. We cannot generate the originally noise-free data points. So this is the final step for building a successful generative model. That is, we use multiple noise levels that grow gradually from smaller ones to larger ones. So suppose we have 3 different levels of noise. We perturb our data set with 3 different intensities of noise. We get the underlying noisy data distributions. And in the context of images, the perturbation process looks like this. After perturbing our dataset, the next step is to learn a model to estimate the score functions for all noisy distributions. So after learning those deep neural network models for those score functions, how do we generate samples this time? We first use long-term dynamics to sample from the most noisy distribution. So we have a bunch of noisy data samples. We use those noisy data samples as initialization and gradually generate samples. So this is for a slightly less noisy distribution. And eventually, we apply the same procedure to the least noisy distribution to generate the eventual samples. And this procedure is analogous to annealing. So that's why we call it annealed long-term dynamics. And this is how this approach works in practice on image generation. So we start from very noisy initialization. We gradually modify the images using long-term dynamics while reducing the intensity of noise. So this is how we generate realistic looking pictures simply from initial random noise. And we can further improve this technique to generate images of a larger and larger resolution, and also to produce images of diverse content. And one very interesting observation in those experiments is that if we use more noise levels, then we achieve better performance. So we can extend this approach to using infinite noise levels. The basic idea is that suppose we have a one-dimensional data distribution, and when we use 3 noise levels, we get a total of 4 distributions because when we use more and more noise to perturb the data, we can convert any data distribution gradually to a white noise distribution, which is much easier to work with. So to give you the intuition, we can use a one-dimensional heat map to represent each of those noisy probability distribution. With more noise levels, we will have more heat maps. And because we want infinite noise levels, we will eventually have infinite heat maps which connect each other to form a continuous 2-dimensional heat map. So this represents an infinite number of noisy distributions. So how do we understand this infinite number of noise levels? Well, the infinite number of noise levels actually prescribe a way to perturb our data point. So this means we can use gradually increasing noise levels to smoothly perturb our data point. So in contrast to using a finite number of noise levels, now this perturbation process is smooth in time. And one important property of such perturbation process is that we can actually reverse the process once we have learned a score function using neural networks. So the reversion looks like this. We start from very noisy images. We gradually remove Gaussian noise from our images, and eventually we can generate nice looking new images. The initial samples are purely white noise, so it's very easy to generate. The final samples do not have any noise, and they are very high quality samples from the data distribution. And this sampling process can be fully determined once we have estimated the underlying score function of our data densities and all noise levels. So this line of approach can create even higher quality images. So here are two samples of human faces, which have resolution 1024 by 1024. They're not real human pictures. They're generated by that noise removal process. And here are more such images generated from the same model with the same resolution. And this type of generation can have lots of important applications. It's an important technique because we can freely control the generation process. So for example, one way to control this generative model is to ask them to generate pictures that only part of the image is known to us. So this is called image embedding. The leftmost column shows the ground truth image. The middle column shows you the masked image, which is known to the algorithm only. The rightmost figure shows all the embedded images by completing the missing portion of the pictures. And you can use the same generative model to generate colorized images. The left shows you some ground truth colorful image. The middle shows the grayscale image. And the rightmost images shows the colorized images by running this noise removal generation procedure. And we can apply the technique to colorize important historic portraits, such as this one for Abraham Lincoln. We can control those generative processes to help us improve medical imaging applications. So let's return to the example of computed tomography. In computed tomography, we have a giant machine that shoots X-rays to human. And the X-rays will hit a detector, which gives the information of human body. So the information is called sinogram. Sinograms are not directly interpretable. No human can understand what they mean. So we need a procedure to convert them into interpretable images. And the procedure is called computed tomography. It's also the image generation process because it generates a medical image conditioned on a sinogram. We want to consider a particular application called sparse view computed tomography, meaning that we want to reduce the amount of X-ray projection as much as possible because X-rays are harmful and we want to protect the health of patients. So generative models are very useful here because if you train them on medical images, they will know what a typical medical image looks like. And as a result, they can help imagine the missing information when you use fewer X-ray projections. And typically, this kind of medical images generated by generative models have comparable quality to those images produced by traditional Pro tools while using much more X-ray projections. So here is one example for computed tomography. And here we only use 23 X-ray projections. In contrast, in practice, traditional algorithms require thousands of projections. So it's 50 times more expensive and more harmful for traditional algorithms. And this is the result of using a traditional algorithm for imaging human body using only 23 X-ray projections. So clearly the picture is blurry. But if we use a diffusion-based generative model, we can create sharp images with only 23 projections. And here is the ground truth. You can see that with only 23 projections, the generated medical image is already very close to the ground truth. While in contrast, the traditional approach would require thousands of projections. And that translates to 50 times more X-ray radiation. And those types of image, text-to-image diffusion models can achieve, so this type of generative models can also be adapted to produce images conditioned on text. And there are lots of successful stories for text-to-image diffusion models. And one example is the imaging model by Google Brain. So I will show you some examples by imaging. And let me switch the shared screen. Okay. So can you see the web browser right now?
Yep, we can see it.
Yeah, so this is some examples from the image model. It is text to image generation model. So the text description is given at the bottom of the picture. So this here, the robot couple fine dining with Eiffel Tower in the background. It's quite realistic. And this one is an art gallery displaying modern paintings. Art gallery is flooded. Robots are going around the art gallery using pedal boards. So clearly those pictures will never exist in the real world, and those were imagined by the model. And this is an extremely angry bird. So all those images are generated using the technique I described to you right before. So those images are generated by first sampling white noise and gradually removing those noise to produce those nice-looking images. And we can also try the DALL-E 2 model. So it is also a text-to-image generative model. So are you able to see the website right now I'm playing with?
Yep, we can see this one too.
Yeah, so this one is an interactive interface. You can basically enter everything here, and it will generate the pictures almost in real time. So here, let's say, let's click surprise me to generate a random text description. And we can click on the generate button. This will create a picture from the text description. So the generation process is slow because it is doing the denoising process internally from noise to data. So you can play with the website multiple times and generate whatever things you want. And let's return to the presentation. So there are numerous other examples of those text-to-image diffusion models. And here are more examples from a very recent one. So this is called Midjourney V5. And it has taken text-to-image generation up to a completely different level. So those are, this is a new image generated by the algorithm. And this person does not exist in real world. It is imagined by the algorithm. And this is another example. It's also generated by the same model about a person, which looks hyper-realistic, but she does not exist in the world. And here, more people generated by the Midjourney V5 model. You can also use it to generate other objects, such as hamburger, food, and baseball, anything you can imagine. And you can create pictures of such level of realism. So you can also do video and audio generation. And here are like two links you can play with. And the quality are also quite good. And all those examples are based on diffusion generation. So now, before we finish the presentation, let me briefly discuss about my story and how I entered the field of AI and how I got my interest in computer science and other things. So when I was very young, around 4th grade, I first developed a keen interest in computer programming. And that was when I was at my primary school. And I found computer programming to be very interesting because it's crazy that you can instruct a computer to do whatever you want just by writing some code. And after that, I played with lots of computer programming languages. Like I learned Visual Basic first, now I proceed to learn C, I proceed to learn Java. And those I also wanted to also learn to solve different computer programming puzzles using those different languages. And later in my 7th grade, I discovered a new passion that was for physics. I found physics to be something very exciting because it allows you to predict what can actually happen in the real world. And it sounds crazy if you understand all the equations, then you can use calculations to predict the future of a physical system. And that is amazing to me. So in my high school, I competed in both physics and informatics Olympiads due to my interest in both physics and computer science. And when I was choosing my major in university, I was hesitating between physics and computer science, but eventually decided to work in physics because I feel the magic of predicting future sounds slightly more exciting to me at that time. And later, when I was doing my major in physics, I worked with a professor who worked on particle physics. And the kind of physics research in particle physics is mostly involved with programming, ironically. So I need to write a lot of programs to analyze the potential trajectory of particles in those large colliders. So when I realized that in actual physics research, people need lots of skills in computer science and electrical engineering. And you probably spend more time in computer science in programming rather than thinking about physical mechanism. So when I realized that, I feel it's probably the time to return to the field of computer science again. And when I was working and when I was picking up computer science again, I spent a lot of time thinking about what could be an interesting subfield for me to work on. And at that time, machine learning caught my attention because machine learning is like physics in computer science because it gives you the power to predict things. It learns the rules to predict new data from existing data. And that combines the perfect advantages of physics and also computer science. So because of this special property of machine learning, I decided to pursue a PhD in computer science and specializing in machine learning at Stanford University. And I have enjoyed working in machine learning and AI so far. And that's led me to take a position as a research scientist at OpenAI. And in the future, I plan to continue work in the field of AI as an assistant professor at Caltech. So you might be curious about working at OpenAI. So here is a video that shows you the what it looks like to work at OpenAI. So let me switch the screen again. So you can see the screen, but can you hear the sound?
No, we can't hear the sound.
So you cannot hear the sound?
No, not the sound, unfortunately.
Let me see if there's anything I can do. Settings.
And while we get the text sorted out, for those who are in the Zoom and on YouTube, you can go to the link provided for the Q&A session.
DALL-E really brings high quality creation.
So can you hear the sound right now?
We can hear it now. We can hear it now.
Okay, let's look at it again. And it's a very good introduction to what it looks like for working on OpenAI.
Imagine the wildest idea that you've ever had, and you're curious about how it might scale to something that's 100, 1,000 times bigger. This is a place where you can get to do that.
OpenAI is building the general technologies that can extend the reach of the human brain and our creativity. DALL-E really brings high quality creations to anyone. Our coding models serve as a coding assistant in tools like Copilot. And GPT-3 is a system that has a robust understanding of language.
Our mission is to create highly capable AI technologies and deploy them to the world for the benefit of humanity in a way that is safe and beneficial for all.
I think that AI will be a technological revolution on the scale of the agricultural, the industrial, the computer revolution, and we have no goal other than the creation and deployment of safe, beneficial AGI. We have a nonprofit that governs everything and the ability to block deployments that would make commercial sense, but we think create safety issues, and our whole structure's around that.
I really like the way OpenAI are trying to build AGI, namely by harnessing large amounts of real-world data to train powerful and supervised models, and then steering those with human alignment to create agents that can actually do useful things.
OpenAI is truly unique in that sense of being able to work in a very nimble fashion, at the same time having all the resources in the world to solve the problems. That mentality is what made it really possible to ship DALL-E.
At OpenAI, we felt very strongly that engineering is an integral part to the success of any progress in AI, and that research needs to be infused with engineering, and engineering needs to be infused with research.
In my first month, I did kind of an outrageously large scaling project. They were like, yeah, we have a piece of software that runs on one computer. Can you make it run on 3,000? And you have 3 weeks. So that was wild.
I don't think you need a specific machine learning background to come here to OpenAI and succeed. I had just taken one class in college. People are very willing to help and teach. And I worked on Copilot, one of the more successful products that are based on ML that people are using day to day.
People are really both friendly and approachable and ambitious. There's this shared sense of we're going to do something very, very big together. We've set our sights high, and also we're collaborating together to make that happen.
The number of times I've been sitting at lunch and you overhear the other team talking about something and you learn a trick from that, just kind of going on the signal of what is everyone else excited about is already a really strong sense of what do I need to pay attention to, what do I need to learn.
For the systems that we're developing to have a big impact, we have to figure out how to make them accessible and how to do so safely. So it's very important to work with a set of people that have diverse experiences, because we're really entering an era where we have to innovate in almost every aspect of society.
I truly believe that the technology we are creating is going to have a really profound impact. Can we create an environment where we have AI and technology broadly amplifying human wisdom, giving humans another resource for connecting with what's actually important to them, what actually gives them meaning? And we need a lot of different kinds of people to make that happen.
Okay, so that's all. And happy to take any questions.
Thank you so much, Dr. Song, for the fantastic, engaging talk. Definitely, I think not only a lot of really good knowledge coming into just giving insights on how diffusion models work for generative AI and how these advancements have evolved over the time, as well as also listening to your story, how you got into artificial intelligence, your past interests, or probably also current interests in physics, so on and so forth. And I really think that just getting to have a glimpse into what it might be like to work at OpenAI, definitely all around fantastic information that I'm sure the audience is very inspired by today. So I'm sure we do have a lot of questions. So just going to the Q&A session, we're just going to hop right in. So for the first question, we have Anonymous asking, Dr. Song, could you talk about the OpenAI residency program and how one might increase the success of participating in such a program without prior AI knowledge?
Without prior knowledge, I think the residency program is about a 6-month internship program. And the goal of the program is, so of course, I'm not the HR, so you may get more precise information from the HR. But from my understanding, that the goal of the program is to help people who do not have lots of prior knowledge in machine learning to get into the field of machine learning and to contribute. And the selection procedure for this program, though, is quite competitive. So I think typically competitors are usually PhD candidates in different fields. They may not be in computer science, but they have to possess strong mathematical skills. Like they might be a PhD student in mathematics, they might be a PhD student in physics, statistics, maybe other scientific fields. So yeah, so if you have a strong passion for machine learning and you have strong mathematical skills or computer skills, I think that's very good for applying for the residency program. Yeah, but I think the HR can provide more precise information.
Great. So someone asked, how did you come to the decision to pursue research instead of working in industry?
Yeah, that's a very good question. I think from the very beginning, I like the idea of doing research. I like trying to explore things that people never knew before. So I did have a time when I tried to decide between going to the industry directly or pursuing a PhD and doing research afterwards. So that was when I was in my sophomore year during my university. And I think the only way to make the right decision is to try both things. So I spent quite some time doing like research internships with different professors. I tried the field of particle physics and tried the field of machine learning. I tried the field of circuit design. And eventually I realized that the field of machine learning is something really interesting. And the vision of pursuing artificial intelligence is also very appealing to me. And in the meanwhile, I also talk to lots of people in industry and ask them what it looks like to directly work in industry. And I try to weigh those different choices after gaining all the information I need. So it turns out that doing exploratory research is more appealing to me, and I can probably generate more impact or produce more contribution to research. So that's how I decided to pursue research.
And definitely all like driving research. So it's always good to look at what you personally are interested in when, of course, deciding to either pursue research or working in industry. And we have another question asking, this is more about the actual contents when you talked about insights regarding diffusion models. So we have someone asking, what kind of data is best for using the diffusion probability models, aside from images? What kind of data is not good for using it?
Yeah, that's a very good question. So usually continuous data is better for diffusion models. So by being continuous, I mean data like images, audio. So those are continuous signals. For discrete structured data like text, graphs, so diffusion models can work reasonably well, but there are better alternatives like autoregressive models. So ChatGPT, for example, is a generative model on text. Right now, it's not using diffusion model at all. But maybe in the future, it's possible that people have extended the idea of diffusion to text generation fairly well. And in that case, we would likely see more adoption of a diffusion model for discrete data.
All right, next question. Does the dimension reduction method on images help before training with the original image data?
So does dimension reduction techniques for images help the training on image data? Is that the question?
Yes, I believe so.
Yeah, so this is also a very good question. The answer is yes. So we indeed need some of dimension reduction techniques to get the method work on extremely large images. So the typical idea is to have a neural network structure called an autoencoder. So an autoencoder contains two parts. One part reduces the dimensionality of an image. So this is called the encoder part. Another part expands the dimensionality of the image back to the original resolution. So this is called the decoder part. By combining an encoder and decoder, you can effectively reduce the dimensionality of any image. So then we can train a model directly on the compressed Latin code generated by the encoder. So this is a much easier problem compared to training the same model on the original image. This is a very common trick in generative modeling research nowadays. So that's an excellent question.
And moving a little bit away from questions regarding data, I wanted to also push out this question, a little more personal on your career and accomplishments. So we have Anonymous asking, what do you think is your greatest accomplishment in AI?
Yeah, so I think my greatest accomplishment is my research on diffusion models. So I'm not the one who first proposed diffusion models, but I think I'm probably the first one who get them to really work in practice. And I managed to get them outperform GANs for the first time in 2019. I think that's the biggest accomplishment I have made so far. And that was I feel that was impressive because people have spent so much time on tuning GANs, and the entire industry and lots of people in academia have spent 4 or 5 years trying to improve the architecture on GANs. And it was surprising that I was able to outperform all the state-of-the-art GANs on a very competitive data set, using like purely on my own of the field. That's something very rare, and I'm still very proud of that moment. Yeah, so that's my answer.
Great. So the next question by Anonymous is, can you explain the basic physics rule behind the diffusion models and why the inverse process of diffusion works?
So the idea of a diffusion is that if you perturb a system like sufficiently slowly, then you would be able to reverse this perturbation. And that also happens in physics as well. So the original diffusion model was motivated by observations in non-equilibrium thermodynamics. And here, diffusion models work because the forward perturbation process, which injects noise, is sufficiently slow. This means the backward process, which also injects noise, can actually reverse the forward process. And this is remarkable because when you're injecting noise, you're actually effectively removing noise because of the reversibility of the forward perturbation process. And yeah, so that's one of the important reasons for those diffusion models to work.
I think it's also definitely really interesting that your prior experience in physics is actually providing a lot, probably for your experience in AI as well. So it's always good to know that there's intersections that can be made between fields and that no career is entirely exclusive of one another. And so we actually have another question from Anonymous asking, I assume this is regarding the solutions that you want to implement. So what are your plans for scaling your AI-based solutions and reaching more people and communities in need? So maybe more about accessibility.
What do I plan to make my approaches more accessible to broader community? I think one very good way to do this is to open source your research. So for all the techniques I talked about and I have researched on before, I hope to make them fully open source. So anyone can download the code and oftentimes download the train checkpoint as well, and generate data as they wish. So I think this is one big part for accessibility. Another part is to make sure those models are as efficient to run as possible. So I know big companies have access to tons of GPUs, and for individual researchers and for people who do not have access to supercomputers, it's important to make sure that those algorithms are efficient to run. So that also is an important part of my future research as well. So yeah, basically 2 parts: open sourcing and doing research on efficiency. That's my answer.
So going back to medical images for a bit. So medical images require a very high accuracy. So this person's question is, what's your perspective on ensuring diffused images capture important details that may not be captured in the original?
Yeah, so this is a very good question. So generative models, while they are effective at reducing like the amount of X-ray projections, they might also hallucinate. And this is also an open question for ChatGPT as well. So the solution is to develop uncertainty quantification techniques. So when the model hallucinates, it should be able to tell us where it has hallucinated. And in this case, we would be able to use potentially more X-ray projections to gain more information, and then to reduce the uncertainty in those regions. So I believe those type of uncertainty quantification research is critical for reliability and for decision-making systems. And it is still under active research. And yeah, I believe there's a lot of things to do, but the future is quite promising.
Definitely, and especially with new people coming in as well. And for instance, everyone in the Zoom right now, people who are looking to get into artificial intelligence. And so we have another question going off of segueing into this one. So we have this person asking, do you think a college student can research diffusion models? And would a college student have computing resources in this research?
Yeah, so intellectually, I would believe a college student will have enough background to research diffusion models. So I believe everyone with the right passion and motivation can research diffusion models. So in terms of computing resources, that's a very good question. So with limited compute, it's probably very hard to research those text-to-image generative models. And those models are actually huge and they require very high-end GPUs to run. But there are still lots of things to explore without excessive compute. For example, lots of like theoretical research, or even some algorithmic research. In order to make sure they work, you first need to implement a prototype on smaller scale problems. And if those prototype works on smaller scale problems, then it's highly likely they will work on large scale problems too. So for some of the small scale problems, it's quite easy to run experiments with them. For example, you might want to do experiments on 2D toy data first. Those 2D toy data sets are surprisingly difficult for modern genetic models to work well on. So those small scale experiments can already generate lots of insights. And you can run those experiments on your own laptop without using GPUs. So I feel even for college students who don't have access to powerful GPUs, it's still possible for them to contribute. And there are indeed lots of things to research on, and I believe everyone can contribute.
So for students looking to kind of get into the AI field, someone asked, could you tell us how to learn AI by themselves? So like what courses, what resources would you recommend?
Yeah, so I think we are lucky to be born in the era of the internet. So you can find lots of resources from the internet. For example, I think almost all the AI courses at Stanford, they are accessible for people outside Stanford University. So you can find course notes, you can find slides on the course website, and they are already very useful for people to get into the field of AI. There are also lots of textbooks that people can try to read about, and some of the textbooks are even for free. For example, the textbook called Pattern Recognition and Machine Intelligence and Machine Learning. So I actually used this book to learn the basics of AI myself. And this book is fully free, and you can download everything from the Microsoft website. So there are also many other resources like the deep learning textbook. You can also download a free version online. And yeah, I believe there are abundant resources on the internet. As long as you want to find them, you will get lots of them. Yeah.
And you just to clarify, what was the first one you mentioned? The machine learning textbook?
Oh, it's called pattern recognition and machine learning.
Interesting. Okay. So we have a few recommendations from Dr. Song there. So of course, if you're looking to study AI on your own, definitely check them out. Free textbooks. And also, for those who are interested in getting into AI, if you're listening to this talk right now, you're already one step closer by being here and being ready to learn. So definitely, we also have a lot of resources, suggestions on our website as well. Of course, check out both Dr. Song's recommendations and the ones listed on our website. And so also, as for just to be aware of your time, Dr. Song, I'm wondering, we do have a few more questions left, but I am aware we are over time. Would you be okay with are you okay on time right now?
Yeah, I think I can take 1 or 2 questions.
Okay, sounds good. We do have quite a lot of questions left, actually.
Okay.
So do you think you would be all right if, because I don't want to do you think you would be all right if I were to send the remaining questions to you?
Sure. Yeah.
Okay,
That
sounds like a
good.
plan. And then we will release the questions along with the transcript. So that way everyone's questions will get answered eventually. And so we have one question sort of looking more at your opinion on the future. So where do you think diffusion models will evolve in the next 5 years?
Yeah, so I think 5 years is super long, and AI researchers are super bad at predicting the future. And so I can only give you an educated guess. I won't say it's a valid prediction. So my thought is that right now there are still some problems with diffusion models, and one problem is efficiency. So efficiency means the sampling process, because it's inherently iterative, and it takes way more compute compared to other models like GANs. And this issue has to be solved, and I believe it is solvable. And so I would say efficiency would be one of the most important research directions in the next few years. Another thing is generation for like discrete data. So I mentioned that text generation, currently diffusion models can work on text generation, but they're not better than autoregressive models, and that's a big issue. So I think in the next few years, people will find the right ways to train diffusion models on text. And beyond text, there are also other discrete data like graphs and molecules. So right now, there are a lot of success on using diffusion models for predicting like the conformations of molecules, which are continuous data. But for the discrete structure itself, it remains to be an important problem to solve. And there are also lots of theoretical questions that we need to answer, like what makes diffusion models to be magically better than other competitors. So right now we don't know. It's we have some hypotheses, but none of them can be rigorously proved. And I think this is also some very important research direction. So further insights on theoretical understanding can not only improve diffusion models, but may also give us hints about how we should design the next generation generative models in the future. And another question is about like, how do we learn good representations from diffusion models? And yeah, so diffusion models are designed for sample generation, but not designed for representation learning. And there are some ad hoc approaches to learn representations, but we still lack a principled approach to extract the useful representations from them. Yeah, so those are a few research questions that are remaining open right now. Yeah, but it's super hard to predict what will happen in the next 5 years. Maybe diffusion models will be replaced by another powerful one in 2 years. That is hard to say.
All right, so just transitioning into kind of the career aspect for a bit. So what advice do you have for students interviewing or looking for a job, kind of this machine learning and AI industry?
So yeah, that's quite a general question. So I would assume the student, yeah, it depends on whether the student have a PhD degree or just graduated from graduated with a bachelor's degree. I would say like also depends on the student's career goal. If you want to work on engineering problems and you want to build real systems and have like lots of impact, then maybe what's important for new grads is to make sure they have strong engineering skills, like they are comfortable with programming, they're comfortable with debugging, they're comfortable with working within a team. And for students who want to do like more exploratory research, then it's important for them to have, I think it's important for them to have a vision about what type of research they want to do, what's important to them, and what is meaningful to them. And then they can try to like become world expert on that direction. And also keep in mind that your research direction needs to be something valuable to the industry if you want to find a job in industry. So if you are a world expert in some direction that is valuable in industry, then of course you will get a good job. And also for both for students who are interested in either engineering or research, I found it's quite important to adapt yourself very quickly to the changing world in the field of AI, because technology develops so fast in the field of AI, and it's important to sometimes just to move on, to give up on some outdated technique, and the mindset of being like learning fast and adapting fast is very important in the field.
Definitely, I would have to agree that flexibility is very important, not just in AI, but also in the real world. And I think just looking at the time, unfortunately, we do have a lot of questions left. So, but just to be respectful and aware of Dr. Song's time, we'll send the questions to him after the talk, where he will answer on his convenience. But otherwise, I do have one more closing question for you, Dr. Song. Just a few parting words for our audience as well. I'm wondering, so as a young emerging expert in this industry, as a researcher, what would you say to students who are interested in just getting into artificial intelligence? Where do you think they can start?
I feel it's an extremely lucky time for us. So we are witnessing lots of breakthroughs, lots of important things happening in the world, and artificial intelligence is playing a big role in like improving humans' life, and it's important for humans' future. So I feel for anyone who are interested in artificial intelligence, it's super lucky for them. And on the other hand, it also means we have super important responsibilities. We need to make sure like every technique we have developed to be beneficial to humanity at large. And I hope this is something that everyone keeps in mind. Like when we are developing those powerful techniques, we need to make sure there are ways to contain them when things go wrong. And we need to be aware of the disruptive effects of some new techniques on the society. So I think this is probably more important than like pure technology advancement. And when some technology advances too fast, it just seems very scary that if this thing goes wrong. So yeah, that's my thought right now.
Definitely. And I think that it's really important nowadays, especially with new generation, to teach emerging leaders and researchers how to ethically utilize AI to solve the world's problems. And with that, thank you, Dr. Song, for a fantastic talk today. Really appreciate your time. I know we went quite over, but we're really happy that everyone thoroughly enjoyed your talk. We had a lot of questions. So definitely, thank you for your time. And for everyone watching, thank you for taking time out of your day to join us with Dr. Yang Song. And we hope that, as always, you're able to take something away, not only from his experiences and also the insights he shared regarding diffusion models and generative AI. A lot of good stuff. So again, thank you everyone for coming, and The replay of this wonderful talk will be posted up on our YouTube channel as well. And if you want to keep up to date for any future talks with Youth AI Lab, and to listen to other brilliant speakers such as Dr. Song, register at our website for more information and follow our socials. Thank you everyone for coming, and I hope everyone has a fantastic rest of their day. Thank you.